Lesson 3 is on efficiency. And efficiency means how much bang we get for our buck. In other words, is what we get out of it worth what we paid for it? How much of the energy that we are supplying goes into doing work, and how much is wasted as heat, as sound, any other thing that's not what we wanted to get out of it? Efficiency is defined as the ratio of energy output to energy input, or the ratio of power output to power input. How much do we actually get out compared to how much we put in? The Greek letter eta, which looks like an N with a tail, is often used for efficiency. So symbol is the Greek letter eta. Let's try that again. It's like an N with a little bit of a tail. Dips underneath the line. And units, it is measured in a percent. So we're going to be finding a percent every single time. So here's your equation using energy. Your efficiency is equal to your energy out on top. Energy out divided by energy in times 100%. So what ratio of our energy that we put in are we getting out? And that is as a percentage. You get the same result if you use the power. So in this case, we're looking at eta efficiency equals P out over P in times 100%. That's going to give us our efficiency in terms of power. Now, if you're looking at the same question, you can use either energy or power to find efficiency, but you don't want to mix energy and power. So you don't want to have energy out divided by power in. You can't combine the two together. So just make sure, actually, when you're doing this, that your units are going to cancel out and leave you only with percentages. So if I have something in joules on the top, that's my energy. If I have something in joules on the bottom, then the joules are going to cancel joules, and that's why we're left only with a percent. If we have something in watts on the top, watts on the bottom, watts cancels watts, and we're left again with just a percent. But if you try to mix joules and watts, you're going to end up with problems, and you won't get to the right answer. So, little note, efficiency is always less than 100% unless you plan on winning a Nobel Prize. In other words, there's always energy wasted somewhere. Usually it's as heat or sound or light that we didn't want to get. That results in not all of our energy that we put in becoming useful energy coming out. So an example of that is a typical household light bulb that transforms energy at a rate of 60 watts. Remember, that means 60 joules per second. The energy is fed into the light bulb. Most of the electrical energy, unfortunately, is transformed into heat instead of light. If you've ever touched a light bulb, it really gets hot. Approximately 57 watts of heat and 3 watts of light are produced by the lamp. So of the 60 watts that goes in, only 3 watts actually gets made into light, which is what we want. We don't really want the heat. The heat is useless to us, so it is wasted energy. And if you plug those numbers into your equation, your 3 watts of power divided by 6 watts equals about 5% efficient. So not very efficient at all. A kettle might transform electrical energy into heat at the rate of 1500 watts. The power ratings of electrical appliances is usually printed somewhere on the appliance itself. So on the light bulb, you can find if it says 60 watt light bulb, 30 watt light bulb, 100 watt light bulb, or on a kettle, you can figure out if it's 1500 watt kettle. Kettles are what heat up water to boiling, or a microwave also has ratings on it. Washing machine, any kind of electrical appliance, you should be able to find the power rating. And again, that's the power that goes in, the power that they take from your house outlet. Let's take a look at an example. Example number 1, a 255 kilogram mass is being lifted straight up at a constant speed by an electric motor. Takes the motor 4 seconds to lift the mass to a height of 12.5 meters. So I've got here the 255 is my mass, 4 seconds, that's my time, and a height, that's going to be the distance that it goes through. So find the work done. This is something you could have done since lesson 1. So work equals force times distance. And in this case, the force is the force against the force of gravity. So I'm going to use the force of gravity. We have to overcome the force of gravity, which is mg, through the distance. So my mass, 255, my gravity, 9.8, and the distance, 12.5. Don't need time to find work. So don't get confused thinking that you have to use all the numbers. Sometimes they'll give you extra information that you don't need. So pull out our handy dandy trusty calculator and figure out what we're working with. Clear this all out. So 255 times 9.8 times 12.5 gives me work, again in joules, 31,237.5. I'm going to write down this entire number first, and then after that I'm going to round it to 2 or 3 sig figs because I suspect I'm going to need to use it again. So this is 31237.5. That is all of the sig figs, not just 2 or 3. Put that away, and that's going to round to for a final answer of 31200. That's in joules. So that is the work done by this machine. Next it says, find the required power. So then we've got power equals work over time. This is from your last lesson. My work was 31237.5. That's why I kept that number. Divided by the time of 4 seconds. I can do that again on my calculator. I'm not going to show you. You can do it. Divide by 4 gets you 7,809. 7,809.375. Again, I'm not going to round it yet, and then I'm going to say my final answer is 7810. Power is measured in watts. That's 3 sig figs. You could also have 7,800. That would also work. So that's watts. Again, these are both the output. This is how much energy is actually going into the process. It's not telling us how much energy the machine is drawing from a circuit. So it says part C, if the motor is using 12 kilowatts of electrical energy, find its efficiency. This is actually kilowatts. This should be electrical power. Sorry about that. Electrical power. And 12 kilowatts, I need to convert. Kilo is times 1,000. So this is 12,000 watts of electrical power. We want to find how efficient it is. So we pull out our equation eta, and then we think, okay, I have power here, and I have another power here. So we must be using the one that has to do with power. So this is P out over P in times 100%. And okay, so which is my power out and my power in? Well, my motor is using 12,000 watts. That's what it's pulling out of the wall, and it's actually producing 7,809.375 as its output and 12,000 as its input. So let me pull out my calculator, and then I'm going to take that number, multiply by 100%. If you ever get a number that's greater than 100%, you can be 99% sure that you've turned the numbers upside down and you need to flip this over, because you should not get a power output greater than 100%. So pull out our calculator, we're going to type in, I'm going to use my second answer button, divided by 12,000 times 100 gives me 65.07, so 65.1%. So how these questions tend to work is you're normally going to calculate the power output, how much energy is actually being useful. In this case, the useful energy was used to lift the mass, and then they will give you the power or the energy input, and you'll need to calculate efficiency. Let's keep going. Example number 2, a girl pushes a 3 times 10 to the Newton box along the floor for a distance of 4 meters. The force of friction is 99 newtons. She then lifts the box straight up at 1.2 meters. So what's going on here? I've got a box going along a floor, and then once it gets to a certain point, it's going to be lifted straight up. So I was going to draw a free body diagram on this box. I've got the force, it tells me the force of friction on the box. So the force of friction is going to keep it from moving. It's going to go in the opposite direction. This is my 99 Newton force of friction. And in order for her to actually push the box along the floor, that means that she has to have an applied force going in the other direction to balance it. So in this case, the applied force is also going to be 99 newtons in order to actually get us moving, overcome the force of friction. When it gives you something like this, she pushes a 3 times 10 to the 2 Newton box. That is the force of gravity. This is actually 300 newtons, is the force of gravity on the box. Instead of giving you the mass and getting you to calculate the force of gravity, they're giving you the force of gravity directly. So that is going to be downwards force of gravity is equal to 300 newtons. So when we come to this point, this also has now a force of gravity of 300 newtons. In order to lift the box off the ground, she's going to have to lift with a force of 300 newtons. Got to balance things out in order to get things moving. In this first example, or the first stage, there is a force upward of 300 newtons. Remember that this is the normal force that comes from anything resting on a surface. So as long as it's resting on the surface there, it has a normal force, but when you start to lift it up, this is now going to be your new force applied, or the force of the girl on the box. So we've got two different things going on. She's first moving the box through a distance of 4 meters sideways. Just gonna put that in a different color. So we're going to move 4 meters left and right, and then we're going to move upwards 1.2 meters. So we've got two different things going on. We're going to have two different works going on in this case. So let's first think about what is the work done in the x direction when we're moving horizontally, when we're moving the 4 meters sideways. Remember that work is force times distance. When we're talking work in the x direction, our force also has to be in the x direction. So I'm going to call this Fx because my d also happens to be in the x direction. So even though there are lots of forces going on here, the force that I'm interested in is the force that's in the direction of the displacement. In that case, it's the 99 newtons force applied that is going in the same direction that my 4 meters is going, that counteracts the force of friction. So 99 newtons is my force in the x direction force applied. And the distance it's moving is 4 meters. So maybe you can do that in your head. I can do 4 times 100 in my head is 400. Subtract the 4 times 1 that are missing would be 396. Work is measured in joules. So this is my work done in the x direction as I move the 4 meters in the x direction. And then I need to figure out how much work was done lifting the box. That's the work done in the y direction as I lifted these 1.2 meters. And so again, we're talking, okay, what force is in the direction of the displacement? That's my 300 newtons applied force. So I'm looking at Fy dy, so my force in the y direction is the 300 newtons times the 1.2 meters upwards. And so I'm going to go 300 times 1.2 is 360 joules. So to find the total amount of work that she has done, I'm going to add those together. So W total is going to be 396 plus 360. Let me see if I can do that in my head. 0 and 6 is 6, 6 and 9 is 15, 3 and 3 is 6, and 1 is 7. So 356 joules would be the minimum amount of work she's put in to move the box sideways and then move it upwards. Notice how we had to take each of these as a separate situation. We moved 4 meters sideways, that was one situation, and then we moved 1.2 meters upward, that was a second situation with different forces. Part B, if she uses, so this is the minimum amount of work that's just put into the situation, so this is going to be my actual useful work, is my work output. This is what I'm looking at. She uses 1200 joules of energy while doing this. In other words, her body burns that much energy. This is going to be the work input. How efficient is this process? So again, I'm looking at eta, which is equal to, I put work here, but work is actually, we're talking joules, it's talking energy. So this is going to be energy out, E out over E in times 100%. So E out, 756. E in 1200 times 100%, and I cannot do that in my head, so I am again going to pull out my handy dandy trusty calculator and go 756 over 1200. Oops. Let's try that again. 756 over 1200 times 100% is 63% efficient. So maybe the trickiest part about this is identifying which is the work out and which is the work in. Again, 99% of the time, it's going to be the bigger number that goes on the bottom. I can't think of any situation where we would put the bigger number on the top. So if in doubt, if you get a number bigger than 100%, flip it over. Should work fine. Example number 3. On a stair climber at the gym, a 58 kilogram person lifts their center of mass up 18 centimeters with each step. So I've got somebody climbing the stairs, and each stair that they climb is 18 centimeters. From here to here, 18 centimeters. Every single step, 18 centimeters. They take 500 steps in 10 minutes, and their muscles are 20% efficient. Then find, first, the rate at which the person does work, and then the rate at which the person uses food energy. So the rate at which this person does work, we're going to use our regular work equals force times distance equation. Now in this case, the person is lifting up their mass, so they're working against gravity, so this is going to be again our mgd, and my mass is 58 kilos, my g is a 9.8, and then I've got 18 centimeters for every single step. So 18 centimeters converts to 0.18 meters. You divide by 100, 0.18 meters. But we do that 500 times. So my total distance is going to be the 0.18 meters times 500 steps. And that's going to be, again, total distance. So with my calculator, I'm going to type in 58 times 9.8 times 0.18 times 500 tells me how much work they do was 51,156. I just realized my calculator is hiding my diagram. Let me put that away for you. Sorry, 18 centimeters every step, so we are going up 500 steps. So this is going to be my answer, and then rounded to 2 or 3 sig figs, 51,200 joules. That's how much work she's doing as she lifts her center of gravity. Now it asks at what rate the person uses food energy. So what I've got going on here, this is my energy output, my useful energy, and I'm asking what is energy input. And the only way to find that is to use our efficiency equation. So I've got here eta equals E out over E in times 100%, and I need to solve this for E in. In other words, I need to get E in by itself. To do that, let's see how I could do that. I need to get E in off the bottom of my equations. I'm going to multiply both sides by E in. So I've got now E in times my efficiency is equal to E out times 100%. And then in order to get E in by itself, I need to divide by eta, divide by the efficiency. So E in, which is what we're looking for, is equal to E out times 100% divided by eta, which was given in my question. In this case was the 20% efficiency. So let's see if we can figure this out. E out, I calculated as 51156 times 100 divided by 20, and see if we can figure out what that's equal to. Pull out your calculator. Mine's gonna cover up, so I'm gonna just leave it. I'm gonna do it in the background. So 51156 times 100 divided by 20 is 255,780. That is in joules. I want to round that to 2 or 3 sig figs for my final answer, so 256,000 joules. Okie dokie, so sometimes you are going to have to rearrange this efficiency equation in order to solve for an unknown quantity. It just depends what you're looking for. Keep going. Another example. Number 4. An internal combustion engine, a gasoline engine that you use in your car, is approximately 18% efficient. This means only 18% of the chemical energy used to operate the motor that you get from gasoline is converted into forward motion, which is the useful energy that we want to get out of it. So a 200 horsepower engine is used for 2 hours. How many watts is the motor rated for? If 1 horsepower is 750 watts. So now we're going to take this 200 horsepower and just do a straight up conversion. We want to know how many watts that's equal to. So multiply by 1 horsepower is 750 watts. Set it up so that your horsepower on the top will cancel horsepower on the bottom. And I need to do 200 times 750 on my calculator. 200 times 750 is going to be 150,000 watts. So that is a mega amount of power that the engine is drawing. Now remember, this is the energy that goes in. Or actually, in this case, this is the power, power that goes in, because we're talking about watts. Not all of that actually makes it into useful energy. How much energy in joules does it produce in that time? So how much energy is actually useful? Well, first let's think about how much energy it actually draws. So this is my power in. So to find energy or work, I know power equals work over time, and I need to find work, so times time to both sides. Work equals power times time. And I've got this 1500 watts is going to be my power. Sorry, not 1500, 150,000 watts. Time was 2 hours, so I need to take this 2 hours and convert it into, watts is joules per second. I need to convert it into seconds. So 1 hour, 60 minutes, and 60 seconds in 1 minute, or you can just times 3,600 is going to give you 7,200 seconds in 2 hours. So I'm going to multiply that, 7,200 seconds. So 150,000 times 7,200 is really big number, 108 followed by 1, 2, 3, 4, 5, 6, 7 zeros. So let's make this 1.08 times 10 to the 9. Talking again, work is measured in joules. So this is how much energy it takes in during that time. But that's not all useful energy. This is energy in. And I need energy out. How much energy does it actually produce? So in order to figure that out, actually all I need to do is multiply by the efficiency. Multiply by the 18% as a decimal. So I'm going to actually take this 18%, divide by 100. So that's going to be 0.18, and then I can multiply that by my joules. So 1.08 times 10 to the 9 times 0.18 to figure out what 18% of this number is. So I'm going to again use my calculator off screen, times 0.18 gets me, what are we looking at, 1.944 times 10 to the 8, I believe. And round that to 2 or 3 sig figs would be 1.94 times 10 to the 8 joules. That's how much energy is actually produced. Still a buttload of energy, but not as much as the energy that was going in. Now, if you can't figure out logically why you should be able to take your energy in and multiply by 18% to figure out what 18%, or sorry, multiply by 0.18 to figure out what 18% is, you can use your efficiency equation. Efficiency equals E out over E in times 100, and we're trying to solve for E out. So essentially what we did was we divided by 100, that was to put it into from percent to decimal, so I have eta over 100, and then I multiplied my E in up to the other side. So this would be then E out over E in, and then I multiplied E in to the other side, so I've got E in times eta over 100 equals E out. But this eta over 100, this is just the 18 over 100 is my percentage as a decimal, so I just took my E in and multiplied by my percentage as a decimal. So if you don't want to show the steps, if you understand why you can multiply by 0.18 to get 18% of my E in, no worries, that's fine. If you want to use the equation, also okay. So this is how much useful energy is produced, and we want to know how much energy is wasted. Well, if this is the total energy in, and this is the total energy that was useful, the rest of it is going to be wasted. And when we say the rest, think subtraction. So 1.08 times 10 to the 9 minus 1.944 times 10 to the 8 will give us our actual energy wasted. So let's see what we get there. So my calculator tells me the wasted energy is 8.856 times 10 to the 8 joules, and to 2 and 3 sig figs 8.86 times 10 to the 8 joules. And that would be final answer. So what have we learned in today's lesson? The efficiency, which is given in a percent, is found by the ratio of the power output to the power input times 100%, or the ratio to the energy output divided by the energy input to 100%. The output is always the useful work or the useful power, and the energy in or the power in is usually given to you in the question, or it's a rating you'd find on the appliance. That's it for today's lesson. Good luck with your homework and your Astri quiz.